Today we're going to be learning how to predict the products of chemical reactions. And so you're going to want to follow along with the worksheet that is labeled Predicting Products of Reactions and Introduction, and also you'll probably have some rules that will help you to do this as well. And so we're going to start by looking at a few examples, and we're going to go in order here. We're going to start with some synthesis reactions and work our way down to decomposition and single replacement and the others as well. So here's the first example that we're going to do together, magnesium plus oxygen. And we see that this is a synthesis reaction because we have two elements and they're basically just combining. And here's the rule that's going to govern that. A metal and a nonmetal combine to form an ionic compound. And so the way that we write that is we just put them together. We have magnesium oxide, which is formed. So that's the ionic compound. Now, like we have to do with all ionic compounds, we need to look at the charges and see if this is really the formula for that ionic compound. So if you have an ion chart, or if you look at the periodic table, you know that magnesium is a positive 2 and oxide is a negative 2, so we don't need to swap those. And so yes, MgO is the correct formula for that compound. Now the next example we have is very similar to this. We have calcium plus sulfur, and once again we have two elements, and the rule is a metal and a nonmetal combine to form an ionic compound. So once again, the same thing, they're going to combine calcium sulfide, and calcium is a positive 2 and sulfide is a negative 2. So those two cancel out, and so the formula is CAS for that ionic compound. Now let's try one that's a bit more complex. Here we have lithium oxide plus water. Now looking at that, some students may have a little bit of difficulty realizing that that's a synthesis reaction. Well, anytime you're adding a compound to water, it's going to be synthesis. We know it can't be double replacement because notice that they both have the same ending, and so it can't be double replacement because they don't have anything to swap. There are no ions to swap out. So this is synthesis, and this is where a metallic oxide, now remember lithium is a metal, so that means lithium oxide is a metallic oxide, combines with water to give a base. And so when we say a base, that means it ends with hydroxide, and it's going to start with a metal. So the metal is lithium, and then the OH would go at the end. And so it's lithium hydroxide. And once again, we have to look at the charges. Right here it says that hydroxide has a negative 1 charge, or you might remember that from the ions that you learned earlier in the year. And lithium is a positive 1 since it's an alkali metal. And so we don't have to swap those, so it's lithium hydroxide, LiOH. Let's try another one that's synthesis. Here we have sulfur dioxide plus water. And sulfur is a nonmetal, and so sulfur dioxide would be called a nonmetal oxide. And so the rule for that is the next one here. A nonmetallic oxide combines with water to give an acid. And like we learned earlier in the year, acids always start with hydrogen ions. And so we're going to start with H. And we know that acids aren't just hydrogen by themselves. They have to have other elements. And we have some sulfur in here, and we have some oxygen in here as well. So we're going to put those into the acid, sulfur and oxygen. Now, the hard part is how many oxygens does this have? And this is one of the toughest parts of predicting the products of reactions. It's kind of hard to say, but usually we find out by adding up the number of oxygens on the left, on the reactant side, and that's equal to the oxygens on the product side over here on the right. So here we have 3 oxygens on the left, 2 right there, 1 right there to make 3, and so we're going to have 3 oxygens on the product side as well. Now, there are some ions involved here, so we need to look at the charges. Hydrogen is a positive 1, as you see right here, so plus 1, and SO3 is the sulfite ion, and it has a negative 2 charge, and you can see that from your ions your ion chart. And so we do have to swap these. So it's H2SO3. So that's the formula for the product here. So that's sometimes called sulfurous acid. Moving along to the next example here. This is obviously not synthesis. Anytime we see one reactant by itself, it's going to be a decomposition reaction. That's decomposition. And if you look at the rules for decomposition, this is the rule that applies. Simple ionic compounds containing two elements decompose into their respective elements. We have 5 rules that we're going to use in this class for decomposition. This is the one that works best. So what are the two elements? Well, of course, silver is one of those. And the other one is oxygen. Now remember, oxygen is a diatomic element, and so when you write the formula for oxygen gas, it's actually O2. So it's going to look like that. Now remember, we're not necessarily writing balanced equations here. It might look a little funny considering we have 2 silvers on the left and only 1 silver on the right, 1 oxygen on the left and 2 oxygens on the right. That's okay. If you really want to, you can go through here and balance this like we learned in our last video, but for this purpose I'm not going to expect you to balance these. So those are our products for this reaction. Now moving on to the next example, we have NiCO3. Now the rule that is going to apply here, once again this is decomposition, we know that when a metallic carbonate is heated, it decomposes to form a metallic oxide and carbon dioxide, CO2. So what's the metal in this metallic oxide? Well, I hope you see it's nickel oxide because that's the only metal in the reactant. So nickel is the metal and oxide, that's our metallic oxide, and CO2, carbon dioxide. And we should look at the charges. Nickel in this formula is +2 because it was +2 over on the reactant side. And oxide, of course, is -2, so it's just NiO and CO2. So that's that example. Let's look at another decomposition reaction. Here we have sodium chlorate, NaClO3. And as you can see on your list of rules, there's a rule for decomposing chlorates. And this is it. When a metallic chlorate is heated, it decomposes to form a metallic chloride and O2 gas, oxygen. So what's the metal in the metallic chloride? Well, the only metal in the reactant is sodium. So our metallic chloride would have to be sodium chloride. And what's the other product? O2, according to this. And of course, sodium chloride is ionic. It's sodium +1 charge, chloride's a -1, so no need to put any additional subscripts. It's NaCl plus O2. And once again, this is not a balanced equation, but if you want to, you can go through and balance it. Our next reaction is this one, NaOH. So we have sodium hydroxide. And in this decomposition reaction, what's the rule that applies here? Well, when some metallic hydroxides are heated, they decompose to form a metallic oxide and water. So once again, what is the metal in this metallic oxide? Well, I hope you said sodium because once again, that's the only metal that's in this reactant. So the metallic oxide is sodium oxide. And the other formula is for water, and we all know what that is, H2O. Now back on the formula for sodium oxide, it is ionic. Sodium is a +1 ion. Oxide is a -2 ion. So it looks like we have to swap the charges, and the formula for sodium oxide is Na2O. And of course water is H2O. So here we have some good examples of decomposition reactions. Let's do another decomposition. Here we have H2SO4. Hopefully you recognize that as being an acid, since it starts with the hydrogen ion. So the rule for acids, as you can see on your list of rules, is this one. When some acids are heated, they decompose to form and there's that's incorrect here, that should say a non-metallic oxide, and water. So what is the non-metallic oxide here? Well, hopefully you see that it's sulfur, because sulfur is the main non-metal in this that, of course, is not oxygen or hydrogen. So it's going to be some form of sulfur oxide. That's the non-metallic oxide. And we all know what water is. That's H2O. Now, how many oxygens are going to be in that non-metallic oxide? Well, once again, just like when we were forming acids a little bit earlier, this is kind of a hard rule to follow. Basically, it's hard to tell, but usually for our examples, the number of oxygens on the reactant side will be equal to the oxygens on the product side. So we had 4 on the left. That means we're going to have 4 on the right. And so since one of them went to water, that leaves us with 3 in this compound. So it's SO3 and H2O. And don't forget, sulfur trioxide, S and O, that's not ionic. So there are no charges to swap. It's just SO3 and H2O. So those are the decomposition reactions. Now our next one, as you can see, is gold plus potassium nitrate, Au plus KNO3. And this is obviously not a decomposition reaction. We have an element and a compound. And anytime we have an element plus a compound, that is a single replacement reaction. And there are a couple rules that are going to pertain here to single replacement reactions. And here they are. An active metal will replace a less active metallic ion in a compound. And we also have a less active metal will not replace a more active metallic ion in a compound. So how in the world do we know what's more active and less active? Well, we have a list, and this list is called the activity series. And this is basically a list of metals in order of greatest activity to the lowest activity. As you can see here, they're appearing on the right side of the screen. And where is potassium? Well, potassium is all the way up here at the top. There's potassium. And where is gold? Well, it's barely on your screen. In fact, I think it got cut off here. It's right down here at the bottom. I'm going to write it in at the bottom so you can see it a little more clearly. There's Au. Gold is at the dead bottom of the activity series. And so if gold is let me roll that back a slide here. If gold is trying to kick out potassium, well, if gold being all the way down here, do you think it's going to be able to kick out something that's all the way above it on this hierarchy of activity? No. I mean, gold is just too low. It's too low of an activity. It just can't do that. So the answer to this one is going to be no reaction. Now, potassium could kick out gold, but it doesn't go the other way. Gold cannot kick out potassium. That's like if I, as a teacher, were to go into the principal's office and say, Mr. Principal, you're fired. Well, it doesn't work that way, does it? It works the other way, but I can't go in there and fire the principal. So the higher an element is on this activity series, the better they're able to kick out ions that are underneath them. Now let's try another single replacement reaction. We have zinc, Zn, plus silver nitrate, AgNO3. And once again, we have the same rules that we're going to use. And let's take a look at the activity series. And once again, we can see if zinc is trying to kick out silver, well, we see where zinc is. and we see where silver is. Can zinc kick out silver? Well, yes it can. It's much above silver. So guess what? Silver gets kicked out. It's all by itself. And the other product is going to be zinc pairing up with nitrate, NO3. And since we have ions pairing up, we have to look at their charges. So zinc is a positive 2 and nitrate is a negative 1. Do we have to swap those charges? Why, yes we do. So the 2 goes down here on the nitrate, and looks like parentheses are needed as well. So it's silver and zinc nitrate. Let's try another one. Let's say we have this reaction, copper plus water. And once again, we have those same two rules that are predominating here. And let's look at the activity series and see if this is going to work. Now, can copper, looks like copper is trying to kick out hydrogen. So here's copper, and hydrogen is above it. So can copper kick out hydrogen? No. And so what's the answer? I hope you said no reaction. And if you think about it, that makes sense, because if you take a copper penny and drop it into a fountain or something else that has water, it does not explode, does it? I mean, basically nothing happens. And so that's a no reaction. By the way, you'll find that that's why a lot of the metals that are used in coins or other things we use to build objects are normally made from things at the bottom of the activity series. Things like lead or tin or iron or zinc or nickel or copper. Now, of course, silver and gold down here can be used for that, but they're just so expensive that we normally don't use those to build things very often. Now, here's another one. Here's another example. We have sodium plus water, and here is the rule that's going to predominate here. This is a special case. Whenever we have group 1 or 2 metals, that's these metals on the first 2 columns of the periodic table, and you add them to water, you're going to make a metallic hydroxide and hydrogen gas. So this is a special type of single replacement reaction. So what is the metallic hydroxide? What's the metal here? Well, once again, it is sodium. So the metallic hydroxide is sodium hydroxide. And the other product is H2 hydrogen gas. And since we have ions pairing, sodium is a positive 1, hydroxide is a negative 1. So those are the products, sodium hydroxide and hydrogen gas. So that's it for the single replacement reactions. Let's go on to the double replacement reactions. Now they're pretty straightforward. Mainly whenever you have a double replacement reaction, the ions are just swapping partners. So we have 2 ionic compounds here. And as you can see in the rule, the ions of those 2 ionic compounds will switch partners, forming 2 new ionic compounds. Now, the way that this will switch is the firsts will always get with the last, and these inside ions will also pair up. So the sodium will pair up with the bromide, and then the calcium will pair up with the chloride. Okay, we always write the metal first. And so it's NaBr, not BrNa. We don't write it like that. Okay, the metal is always written first. Likewise, it's CaCl, not ClCa. That's wrong. Now, notice that this subscript of a 2 in bromide did not travel across. That's because we have to look at the charges to see what the new subscripts are going to be. So we know that sodium is a positive 1 and bromide is a negative 1, so there's no swapping there. It's just NaBr. The same thing over here with the calcium and the chloride. Calcium is a positive 2 and chloride is a minus 1, so guess what? We're going to have to swap those. So CaCl2. And so those are the products. So let's try another double replacement. It's very similar. We have silver sulfate, Ag2SO4, plus aluminum chloride, AlCl3. And once again, the outside ions are going to pair up, and the inside ions are going to pair up. So I'm going to write this on the next line so we have a little bit more room here. So one of the products is going to be Ag pairing up with Cl, and then the other one is going to be Al, aluminum, pairing up with sulfate, which is SO4. And we have to look at these charges again. The silver is a +1, and the chloride is a -1, so those don't swap anything. The aluminum is +3, and the SO4 is sulfate, that's -2, and it looks like we have to swap those. So it's Al2, and then we have a 3 for the SO4, and we need parentheses. Now if I'm going too fast, if you don't see where these charges are coming from, you need to look at your ion chart. And so you can download a copy of the ion chart off my website, or you can get one from the teacher in class, or look at your textbook to find these charges for ions. You learned these several months ago, and of course you might need a refresher on some of those. Here is another double replacement reaction. It works the same way. We have the insides and the outsides. So the outsides get together. The H will pair up with OH, and then the insides get together. And so K gets with Br to make potassium bromide, and then H pairs up with OH, and we can write that as HOH, but most people just write that as H2O, or water. And so this is the same thing as any other type of double replacement reaction. We can look at the charges for KBr, +1, -1, those cancel. So this is kind of a special case of a double replacement reaction, though, because in this case we have an acid and a base. HBr, hydrobromic acid, is of course an acid, and potassium hydroxide, it ends with hydroxide, so this is a base. And so one of the products, of course, is water, and the other product is a certain type of ionic compound. We call that a salt. Now, most of the time when you think of the word salt, you think of the sodium chloride that you sprinkle on your French fries, but really in chemistry the word salt can refer to many different ionic compounds. Almost any ionic compound that is the product of an acid and a base reaction can be considered a salt. Now this special type of double replacement reaction, when an acid is reacted with a base, is called a neutralization reaction. So you've probably heard that word before, and that's what this is. So moving on to the last type of reaction, which is combustion. Here's the first example, and there's really only one rule for combustion, and when it's a complete combustion of a hydrocarbon and oxygen, you always have carbon dioxide and water. Now, I think that's probably the easiest type of reaction, as long as you can identify combustion. You have a hydrocarbon plus O2. The products are always the same, CO2 and water. So we like to see those on the test, don't we? Here's another example. We have C8H18, which we call octane, and we add that to oxygen gas and undergo a combustion there. What are the products? They are the same, carbon dioxide and water. So this was a quick tutorial of how to predict the products of reactions. Now, it is a little bit of a challenge to learn these rules, but once you learn the rules and you're able to recognize which rule applies with which reaction, and you get some practice, you'll hopefully get pretty good at predicting the products of chemical reactions.